Today, we're going to dive into a pretty remarkable piece of technology. It gives scientists what is essentially a superpower, the ability to see things that are, well, fundamentally invisible. It's called atomic absorption spectroscopy. So let me ask you a question. How would you even begin to find a single toxic atom? Say, a tiny speck of lead or arsenic just floating around in a regular glass of water. I mean, that sounds completely impossible, right? It's like finding a needle in a haystack the size of a planet. Well, this machine right here is how you do it. This is an atomic absorption spectrometer, or AAS for short. And it is a seriously powerful tool designed to solve that exact problem, pinpointing and measuring tiny, tiny concentrations of specific elements, even down to a single atom. So how in the world does this machine pull that off? To really get it, we need to look at the fundamental physics at play. And it all comes down to a really cool property of how atoms absorb light. This diagram here, it lays out the entire journey from start to finish. You've got a specific light source, then the sample gets vaporized into individual atoms, those atoms soak up some of that light, and a detector on the other side measures what's left. It's actually a pretty straightforward process, and the whole thing works because of one very simple idea. The easiest way to think about it is like this. Every single element on the periodic table, calcium, iron, lead, you name it, has a unique favorite color of light that it just loves to absorb. A calcium atom won't even notice the favorite color of a lead atom, and vice versa. They're incredibly picky, which is exactly what makes this technique so unbelievably powerful. Now, here's what's so fascinating. At the temperatures inside this machine, more than 99% of the atoms in any sample are just chilling out in their most stable, resting state. Scientists call this the ground state. So think of them as just calm and ready. They are perfectly primed to absorb that one specific wavelength of light, their favorite color. And this is so important because it gives us a massive, predictable number of atoms to measure, which makes the results incredibly reliable. So, if you put all that together, you get our official definition. Atomic absorption spectroscopy is a technique for figuring out the concentration of a specific metal in a sample just by measuring exactly how much light its atoms absorb. That is the core principle in a nutshell. All right, so now that we've got the basic idea down, let's actually go inside the machine and follow a sample on its journey, all the way from a liquid to a final measurement. The whole process really breaks down into 4 key stages. First, you need a very specific light source. Second, you need a way to turn your sample into individual atoms. Third, you've got to filter the light. And finally, you need a detector to measure the result. Okay, so the whole journey kicks off with a special kind of light source. It's called a hollow cathode lamp. Now, the brilliant part is that the cathode inside this lamp is made of the exact element you're looking for. So if you want to find copper, you use a copper lamp. This guarantees that it emits that precise favorite color of light that only copper atoms are going to absorb. It's so clever. Okay, so we've got our special light. Now we need to get our atoms ready. The liquid sample gets sucked up into something called a nebulizer. You can think of it like a perfume atomizer, and it turns the liquid into a super fine mist. This mist then gets mixed with fuel and sprayed into a long, thin flame. The intense heat instantly vaporizes the liquid and just blasts apart all the chemical bonds, creating this perfect cloud of free individual atoms right in the path of our light beam. And this is where the magic happens. The beam of light from our lamp shines directly through that cloud of atoms. As it passes through, the atoms of our target element, and only our target element, see their favorite color, and they absorb some of that light energy. And here's the crucial part. The more atoms there are in that flame, the more light gets absorbed. Simple as that. Now, after passing through the flame, the light hits what's called a monochromator, which is basically just a really fancy high-tech filter. Its only job is to block out all the other stray light, especially the bright glow from the flame itself, and make sure that only our specific wavelength gets to the detector. The detector then measures the final intensity of the light. So by comparing the light that went in to the light that came out, we know exactly how much was absorbed by our atoms. Okay, so the detector gives us a raw value for the light that was absorbed, a number that's called absorbance. But how do we translate that into something that's actually useful, like parts per million? Let's take a look at the art of measurement. It all boils down to this one simple rule. The amount of light that gets absorbed is directly proportional to the number of atoms in the flame. More atoms, more absorption. Less atoms, less absorption. It's this simple, reliable relationship that is the foundation for turning a measurement of light into a concrete number. To actually make this relationship useful, here's what scientists do first. They perform calibration. They create a set of samples with precisely known concentrations, 1 part per million, 3 ppm, 5 ppm, and so on. They run each one through the machine and they plot its absorbance against its concentration. And what you get is this beautiful, perfect straight line known as a calibration curve. And here's the actual data that builds a curve just like that. You can see that clear, predictable relationship, right? So now we run our unknown sample, and boom, it gives us an absorbance of 0.639. All we have to do is find that value on our calibration curve, and we can trace it right back to a specific concentration. It's a really elegant and precise way to turn a measurement of light into a hard number that means something. So, this is clearly a very clever piece of science, but why does it really matter? Let's talk about why this technology is basically a quiet guardian in our everyday lives. So, where did this all come from? Well, the technique was first cooked up back in 1955 by an Australian physicist named Alan Walsh. By the 1960s, the first commercial machines started popping up, and since then, it has become an absolute cornerstone of analytical chemistry all over the world. And its applications are, well, they're everywhere. In environmental science, it's checking for arsenic in our groundwater. In medicine, it's analyzing metals in our blood. In agriculture, it makes sure our soil has the right nutrients. It's used for food safety, mining, manufacturing. Seriously, it's working behind the scenes in almost every industry you can possibly think of. And get this, the technique is incredibly versatile. It can be used to measure more than 70 different elements. All a scientist has to do is swap out that special lamp for one made of a different element, and just like that, they're ready to analyze something entirely new. So, from the water we drink to the food we eat, atomic absorption spectroscopy is this quiet guardian, protecting us every single day. It kind of makes you wonder, right? What other invisible science is out there shaping the world around us right now?